Hello again, ladies and gentlemen, and welcome to the next edition of Algebra 2 Notes with Miss Faust. Today we're going to continue talking about piecewise defined functions, so hopefully you have this packet handy. We did the first part of it last time, and we're going to continue working with it today. So I'm going to magically make it turn to, ta-da, explain 3, which is modeling with piecewise functions. So last time we talked about how we make a graph of piecewise functions. Remember, piecewise functions are basically just multiple functions that we're graphing in the same graph, and we're restricting the domain of each one of them to put together a story. Like I said before, I like these because these are really realistic kinds of problems, things that might happen, you know, a graph that might actually be created. So this is some examples using real world problems, and then we'll do one more thing today and we'll be good to go. So by now you should have this out. You should have it open to explain 3, modeling with piecewise defined functions. And the idea here is that real world situations can be described by piecewise functions, as Miss Faust already told you. So example 3, write a piecewise function for each situation, then graph the function. So the first one you'll see is already done for us, so I'm just going to talk about it a little bit. On her way to a concert, Maisie walks at a speed of 0.03 miles per minute from her car for 5 minutes, waits in line for a ticket for 3 minutes, and then walks to her seat for 4 minutes at a speed of 0.01 miles per minute. So she walked very slowly to her seat and more quickly from her car to the line. Maybe it was raining. Who knows? So what we're going to do is express not the Maisie's distance. Hello, typo. I didn't make this, by the way. Express Maisie's distance traveled, d in miles, is a function of time, t in minutes. So this 0 to 5, we know because it told us in the beginning that she walked for 5 minutes from her car. We know the slope of that line is 0.03 because it tells us the speed was 0.03. And we know she started at her car. So that's why the y-intercept is 0. So that's how we get this 0.03t with no y-intercept to add to it. The next thing we know, she waits for 3 minutes. So she started waiting after 5 minutes, and then she waited until 8 minutes because 5 plus 3 is 8. So when her times were between 5 and 8, her slope was 0. She wasn't moving. And her distance was 0.15. And the way that we would find that is if we look back at this function, and we do 0.03 times 5, that's going to tell us how far she was from the car when she waited in line for the tickets. And when we do that, we get 0.15. So we know that that whole time she was waiting, she was at 0.15. She wasn't going any further away, so that gives us that function of d of t equals 0.15. Finally, we have the last 4 minutes, so that's 8 to 12. Told us her really slow speed, 0.01. That began at 8 and 0.15. So really this equation, you have to do a little bit of work to find that. I'm going to do it off in the left-hand margin here so you can see. So what we would know is that after 8 minutes, she was at 0.15. So 0.15 equals the speed, 0.01 times 8, plus whatever the y-intercept is, because we're trying to find the y-intercept. I'm just showing you where this 0.07 came from. So 0.15 equals 0.08 plus b, subtract 0.08, subtract 0.08, and 0.07 equals b. So the equation for that last 4 minutes is 0.01t plus 0.07. So we're just taking all of this information and writing it together in the piecewise function notation. And then over here we drew a graph for it. So at 0 minutes, 0 times 0.03 is 0, so that's where that point comes from. After 5 minutes, we already did 5 times 0.03, it was 0.15, so that's where that point comes from. From 5 minutes to 8 minutes, it just stays horizontal. So here we know she was increasing constantly. There we know she was staying horizontal. And then 0.1t plus 0.07 from 8 to 12. So you could do that a couple ways. You could say, okay, between 8 and 9, it goes up by 0.01. Between 9 and 10, it goes up by 0.01. So you could do it going up by 0.01s, or you could find out what it is at 12. I'd probably do that. I'd do 0.01 times 12 plus 0.07, just plugging those in from this equation. I get 0.12 plus 0.07, which is 0.19. Yeah, 0.19. So that's where that last point goes at 12 and 0.19, and we connect those. So that's how we get a graph of this function. So we're going to go through the second one together, have a little bit of think time in this one. So we have a college student on his way to class from his dorm room. He walks at a speed of 0.05 miles per minute for 3 minutes, stops and talks to a friend for 1 minute. To avoid being late to class, runs at a speed of 0.10 mile per minute for 2 minutes. So we're going to write the function basically like we did up top. So from 0 to 3, the slope, remember m is slope, the slope was 0.05 miles per minute, and the y-intercept was 0. He starts at his dorm room. So our formula, d of t, is 0.05 t. From 3 minutes to, how long did he stop and talk to his friend? 1 minute. So 3 plus 1 is 4. So between 3 and 4, the slope is 0. He is 0.15 from his dorm room. And again, we would do that by coming back here and saying, well, after 3 minutes, 0.05 times 3 is 0.15. It's not always going to be 0.15, happens to be in these two examples. From 4 to 6, his slope is 0.1 or 0.10, and that began at the 0.4 and 0.15 because that's where he was at that 4th minute. So y equals 0.1x minus, and we have to figure out this y-intercept again. So again, to figure out the y-intercept, we know a y, we know an x, so we're going to say 0.15 equals our slope, 0.1, times 4, because it took him, he started at 4 minutes, plus whatever our y-intercept is. So 0.15 equals 0.4 plus b, subtract 0.4 on both sides, and you get negative 0.25 equals b. Well, they already put the negative in for us, so we're just going to put a 0.25 here. So we've got all the pieces now of the function. We've thought about it a little bit in context. So this first one is 0.05 because that's the 0 to 3. 0.15 from 3 to 4, and 0.1 minus 0.25 from 4 to 6. So our points from 0 to 3, they've already graphed that part for us. Gee, thanks. 0.15, so it stays the same until we get to 4. And then here we have a slope of 0.1. So if I know this is 0.15, which I knew from right here, right? So I know this is 4 and 0.15. If I want to go up by 0.1s, so 4 and 0.15, so I go up by 0.1, so I get to 0.25 and over 1, and then up to 0.35 and over 1. So I'm going up by 0.1 each time. And notice in this graph, each block is 0.1. So that's a pretty easy way to do it. Up by 0.1 over 1, up by 0.1 over 1, and we're done. Okay, so that gives you a good idea of how you would create that graph. Moving on to example, to explain for, you can actually skip the bottom of that last page. I just think that you've seen enough examples for now, and I don't need you to take the time to do that on your own. We'll talk about it more in class if you need it. So we get to building the functions from the graphs, and really this is like the inverse, pardon the bell, reminds me to move the pointer. There we go. Okay, so this is the inverse of what we've been doing. Before we've had the function and we're drawing the graph. Now we have the graph and we're drawing the function. So you can find the function rules for a piecewise function when you're given the graph of the function. So we're writing an equation for each graph. So basically when we're writing an equation for each graph, we've got to look at how many pieces of the graph we have. So in this one we have 2 pieces. So we need to think about what the equation is for this piece, and we need to think about what the equation is for this piece. And then we need to think about where the break is. So this piece, right, this piece on the left, that's just a horizontal line. So remember, a horizontal line is always just y equals whatever the y value is. So the y value here is -1. So that just has an equation of y equals -1. This one on the right starts here. It's a linear function, so we need a slope and y-intercept. So from here it goes up 3 and over 1. So we know our slope is 3. And our y-intercept we can't see right now, but if you were to continue that line, you would go down 3 and back 1. And you can see pretty easily that the y-intercept would have been -2. Okay, so they did that a different way. They actually used the slope formula, and then they used a point, and they used point slope form. You get the same thing. You still get 3x minus 2. Okay, so then what we do is we write the function. And because this function has two pieces, we're going to write it in two function pieces and two domain pieces. So the -1 is on this side of the line. So what we want to do is we want to look at where this falls. So if we look right here, that dotted line I drew is at x equals 1. So since the dotted line is at x equals 1, 1 is the number I'm going to use. But then I look and I say, okay, this is everything to the left of 1. Everything to the left of 1 means x is less than 1, not equal to, because it's an open circle. We look at the second part, it's starting at 1, so the 1 goes here. It's everything to the right of 1, so to the right of 1 means it's greater than, and it's a closed circle, so it's greater than or equal to. Okay? So now we can go on to B, and in B we have to look at, again, we look at the two parts of it. So here, if we start by looking at this one, find the equation for the ray on the left, they tell us. So the ray on the left is this part. So that part of the graph, I can see from this that the slope is 1, but I'll go ahead and use their method. Actually, what points are they even using? They use -1, 1, and they want us to use another point. Okay, so let's just use this one. So our points will be -1, 1, and -2, 0. So then 1 minus 0, because we subtract the y's on top, -1 minus -2. 1 minus 0 is 1, -1 minus -2 is 1, so the slope is 1. That's the same thing I just told you. So that gives us the slope. We're going to skip this part. We're going to find the y-intercept from the graph. If you've learned point slope form before and you love it and you want to use it, go for it. We have a graph though. Why make our lives difficult? So if I extend that, it would go through 2. So y equals 1x plus 2 is the equation for that part, or just y equals x plus 2. I like to keep track on my graph too, because then the next steps are a little bit more straightforward. The other part of the graph starts here and is a horizontal line going that way. So a horizontal line going that way means it's at 1, 2, 3. So that one's at y equals 3. And then the last thing I'm going to think about is where this break point is. So this break point in this one, I don't want to switch colors again, sorry, I'm just doing it in this color too. That break point is at x equals -1. So that's going to help me with the rest of the function. So the equation of the horizontal ray, that's the pink one here, is y equals 3. So the equation for the function is y equals 1x plus 2 if x is less than or equal to 1, and it's less than or equal to 1 because it's a colored dot. -1, I'm sorry, less than or equal to -1. It's a colored dot and it goes to the left. Greater than -1 because it's an open dot and goes to the right is where it's 3. So let's do one more together, and then I think you guys will have a good idea of how this works. So again, in this function, I have two pieces. So I always start by writing out this part. So I know my function parts are going to go here, and my domain parts are going to go here, because that's what piecewise functions are. They're just functions with restricted domains. So we're graphing multiple functions at once. So I'm going to start on the left. Oh, look at that. They gave us the y-intercept. We can count the slope. It goes up 1 and over 2. So this part is y equals 1/2 x minus 4. That's my first equation. My second equation, just this little teeny tiny snippet of an array here, but we can see that it's at y equals 1. So I'm going to write y equals 1 there. If this had some slope, I'd have to find the y-intercept. Again, I could just continue it on the graph to see what the y-intercept would be. But it's a straight line, so that's easy. This one's almost too easy, but who's complaining, right? We look for where the break is. The break in this one, again, is at x equals 4. So I know that the left part is going to be x is less than 4, but then I have to think about the endpoint. Endpoint's closed in, so it's less than or equal to 4. I look at this part, this is going to be x is greater than 4, and it's open, so it stays just greater than. And that makes sense for a function. They couldn't both have closed circles, or this wouldn't be a function. And with that bell, we are done for today with our Algebra 2 notes. Thank you for tuning in, and have a wonderful day. Woo!